So what I'm going to focus on for the next hour and a half probably is what you heard a lot about yesterday, this idea that oSCR is built around the multi-session likelihood structure. And the focus of today is just, first of all, introduce what we mean by multi-session models and multi-session data, and then couple that with some background of what multi-session models are useful for, why you'd want to use them, how you would do these things in practice, and then show an example using some of my own data on how you'd fit some of these multi-session models. Now, as you might guess, there's when you actually start introducing different groups of populations or different populations that you're interested in, all of a sudden you kind of open up the gates to ask some different questions, some new hypotheses arise. So although this lecture is going to be on multi-session models, what it does lead into is how to do things like multi-model selection, how to choose amongst a bunch of covariates, and I'm going to introduce some new helper functions. And at the end of the lecture, I'm just going to go back and talk a little bit about the trap deployment file and how we can add covariates and trap operation information based on a couple of questions that came up this morning or earlier on today. Okay, so what do we mean by multi-session SCR models? Well, the thing that you probably know in your own experience is that data often come from independent sessions. And when we talk about sessions, really what I'm talking about here is different strata. So we can think about spatial sessions. So in this figure here from a PhD student of mine, what he is doing is he's interested in estimating some state variable in each one of these reserves in Southern Africa. And that state variable, we want that to be reserve specific, but we also want to be able to test things like, are there differences among these reserves? And we want to introduce covariates like, are there lions present? But essentially this is a good example of a spatial session where each of these reserves are independent reserves, but we might want to analyze all of these things together. We can also think about sessions as being temporal sessions. So sometimes you might be monitoring a population over time from one year to the next. And we spoke a little bit about this yesterday, where you might be violating the assumption of closure by collapsing 3 or 4 or 5 years together and analyzing it all together. Well, a natural framework for dealing with that would be to treat each year as a session, and then model session specific parameters where time or year is the session. You lose some of the independence between years, so you ignore the fact that individuals are the same individuals are in each year, but it is a convenient way to deal with these temporal sessions. And the bottom line here is that what we want to do is try and understand whether there's any changes in time, trends positive or negative, or whether there are differences among populations in space. So ideally what we want to do is take this multi-session data and analyze it all together. So the first question is, how do we do that? And the second question, of course, is why should we even be thinking about doing that? So the how, first of all, it won't surprise you that the how is basically we can analyze these data structures in this package oSCR. And for more background about the mathematics or the statistics behind the multi-session sex-structured likelihood, that's all written down in the ecography paper that you have access to. But the idea is that we've formalized that session structured likelihood within the oSCR package, so it makes it very easy to fit session specific models and sex specific models for that matter. The next question is, why should we think about doing that? Why do we want to analyze all of these kind of multi-session data sets all together? Well, there's a few reasons. First, we can start to share parameters across sessions, so we don't necessarily have to treat those as independent. Maybe we can make a reasonable assumption that space use for the species is fairly constant across space. So by setting sigma to be constant across space, we actually are able to effectively pool data to start getting better estimates of shared parameters. And we can think of that as being more efficient use of sparse data. So there might be some sessions that really have very, very little data, and they might not be able to be analyzed on their own. So what we can actually do is integrate them into a joint model and utilize that data rather than throwing it out. And adopting a multi-session approach also gives us a formal framework for hypothesis testing. So we can, because we're working in the likelihood-based analysis here, we can use things like AIC to compare models and to formally test for differences among sessions. So are there temporal trends, or is there temporal variation? Is there differences in density or space use or detectability over space or over time? So what I want to try and reinforce today is that the workflow, this repeatable workflow that I spoke about yesterday, or this fairly straightforward workflow that I spoke about yesterday, is pretty much consistent regardless of which models you want to fit. And hopefully what you'll get from the next few slides is that actually fitting multi-session models in oSCR is quite as straightforward as fitting single-session models. The reason this is because the likelihood function, and in fact the whole package is built around this idea that data can be structured both by the session in space or time, but also by sex if you have information about sex. So the whole model fitting architecture is really driven by the fact that we would like to model variation among or test hypotheses about variation among sessions or groups among populations. So the likelihood function is built around the multi-session structure, and the data structures, the oSCR frame and the state space objects, are also based around or have this multi-session idea at their core. And that's why you always see these lists. So I didn't talk about it much yesterday, but almost everything you look at is packaged up as a list. And the reason we do that is that we package up session-specific information as a list. So even if there's only a single session, it's still packaged up as a list because it has that general, this general structure. And by building it around this general structure, we're able to have built-in options for modeling. So like I said, the process or the workflow is very, very similar to what we saw yesterday. Instead of creating an oSCR frame, we're just going to create a multi-session oSCR frame. Instead of creating a state space object to an SSDF, we're going to create a multi-session SSDF. We're going to use exactly the same helper functions to do that. And once we do that, we're able to specify specific models. So we can start fitting models without any covariate information, just using or leaning on the multi-session structure. We're going to start being able to fit models that compare formally fixed parameters versus session-specific parameters. And we can do that for each of the core components of the spatial capture-recapture model: the density, the baseline detection, and the space use. So now I'm going to walk through, with no examples just yet, I'm just going to walk through this workflow and just show you what the differences are for the multi-session approach. So the first thing we do, as we did yesterday, we're going to use data to oSCR, this helper function, this really critical helper function is going to ball up all of our data into an oSCR frame. So just like yesterday, we're going to have this EDF, this encounter data frame. Now, this isn't going to change at all. In fact, if you think about it this way, if you did 2 spatial capture-recapture studies in 2 different reserves and you collected EDFs, they're all going to have the same columns. They're all going to have a session column, like the park ID, for example. They're going to have the trap information, the occasion information, and the identity of the individual. So it makes sense that regardless of how many sessions you have, all of these EDFs can sit nicely on top of each other because they all have the same, they all have common columns. So in fact, our multi-session EDF is just the same object, but just with session-specific EDFs are binded on top of one another or appended on top of each other. And then we always have the session column. So we're going to use that session column to identify which session these particular captures came from. What isn't consistent between sessions is the trapping effort. So you're going to see this in a little while with the Salamander data. I can set cameras out for 90 days over in this park and maybe 65 days over in this park. I could use 35 cameras over here and 25 cameras over here. So what starts to happen is that these trap deployment files can start to take on different shapes and different dimensions, a different number of columns and a different number of rows. So for the TDFs, they're not going to neatly stack on top of one another. That's why we keep it as a list. So we're going to package up all of our session-specific TDFs in a list. So really, this is the only thing that's changed so far. Instead of having one trap deployment file for the single session data object, now we're going to have a TDF for every session that's in our analysis. And for every TDF, there's going to be a chunk of this EDF that has the session identifier. Then for the column identifiers for the EDF, this is just going to be the same. So what column is your session? What column is your session column? What column is your ID column? What column is your occasion column? And what column is your trap column and sex column? And then down here, we're going to get these two new objects. So we had K before. That was how many occasions, how many trapping occasions did you have in this particular study. Now, instead of being a single value, there's going to be a vector. So this is going to, if we had 3 sessions, there's going to be the number of occasions for each of those sessions. So 90 days over here, 90 occasions, 25 occasions, and 35 occasions. For a 3-session study, there's going to be 3 values, and those values are going to correspond to how many occasions were in each of those sessions. And then the same thing here for the number of traps. N traps is now going to be a vector, and the length of that vector is going to be the same number of sessions that you have. So if you have 5 sessions, there's going to be 5 numbers here, and those numbers are going to correspond to how many traps you had out on the landscape, or how many detectors you had out in the landscape in each of the sessions. So once you've extended this TDF list to include a list for every session, you've made sure that all of your session data have been appended here in the EDF. And then you've also made sure that you've told data to oSCR how many occasions per session and how many traps per session. You can just run this line of code and we'll be right back to where we were yesterday. We've created this Spatial Capture-Recapture data object within which you can extract the oSCR frame. So this looks very much like it did yesterday. So then we also want to create that. With the second step in our workflow was to create the state space object, to define and create the state space object. So yesterday I spoke about 2 ways of creating this state space object. First was doing it externally or manually, where I was just basically making a data frame and giving it a class. So I'm not going to talk about that way because I prefer to use the functions available within the package. I'm going to use the make SSDF helper function here to create a multi-session state space object. So the really nice thing about this is that if you pass a multi-session SCR frame to make SSDF, then you automatically make a multi-session state space object. So if you provide a multi-session SCR frame, a multi-session SSDF is returned. So that's a nice thing. So we don't actually have to know anything else here apart from the fact that what we're going to do is supply this multi-session SCR frame that I spoke about in the previous slide. We're still going to define a buffer around the traps, and we're going to still define a resolution around a resolution that defines the space between the points of the mesh. And just as a reminder here, just because it's very good to bear this in mind, that these decisions are things that you need to make. So the buffer, there's some rules of thumb about what that buffer should be, 3 to 4 sigma. There's some rules of thumb about what that resolution should be. It should be approximately sigma or below. The MMDM that you can actually get from your SCR frame, the mean maximum distance moved, can be used as an approximation of the sigma value. And we do recommend that you just make sure that, that if you change those values, your parameter estimates aren't sensitive to the definition, the parameters that you choose. Now, another thing we have to bear in mind here for the multi-session structure is that we're just providing one buffer value and one resolution value, which is to say we're basically specifying state space characteristics that are consistent across all sessions. And you can make arguments for not wanting to do that, and it would be very easy for us to extend this function to allow for different size buffers and different resolutions for each session. Okay, if I go off on a tangent here, if we imagine that we were thinking about two different species as a session for some reason, then maybe we might want to consider different buffers and different resolutions. Okay, so the workflow was create this oSCR frame, create the state space object, and now we can go ahead and start fitting models. These 3 lines of code that get us to the point of spatial capture-recapture analysis. So to fit multi-session models, it's exactly the same as it was. We use the fitting function, oSCR.fit. We still need to specify the models, but now what models are available to us? This is where we kind of move beyond that SCR null model that we saw yesterday, the null model, ~1, ~1, ~1. What we can actually do is utilize the fact that we know that there's session structure, we know the likelihood is set up to deal with that session structure, and we know the data objects are set up to deal with that session structure. So now we can have that SCR null, but we can also specify session-specific parameters. So if we really are interested in comparing 2 population sizes or the density of 2 populations that we consider to be independent sessions, then we can fit that model now that we have the structures in place. And not only can we fit session-specific parameters, models for session-specific parameters, but we can also use combinations of session-specific or fixed parameters. So here's an example of that. These are the models, this null model that I spoke about yesterday. Essentially, we're going to define each sub-model, SCR sub-model. So the model for density, we're going to use ~1, which is essentially an intercept-only density model, a log linear model with an intercept only. And then we have this logistic regression, which is specified by ~1. So we're estimating an intercept only. And then we have the log linear model with only an intercept for sigma. That's because these two need to be non-negative, and detection probability here I'm talking about needs to be bound between 0 and 1. So we use these link functions, and we have these intercept only models. So we have no covariates here, so we don't have any slopes. And then the way we specify these models in oSCR is just like this. This is what we spoke about yesterday. So a couple of things we need to know about what happens when we have a multi-session model and we specify the ~1. So like I said, it's an intercept-only model, but what we're doing if we have a multi-session structured data set is that by specifying ~1, we're assuming that there's no difference between the sessions. So we're essentially fixing that parameter. We're saying both, in a 2-session model, we're saying both densities are this, and both detection probabilities are this, and both space use parameters are this. What we can also do, like I keep saying, we can lean on the fact that the whole package is built around the session structure. So if you specify ~session in oSCR, it immediately recognizes that you want to fit a session-specific model. So here, the only difference between the previous slide and this slide is now we're adding session-specific covariates. So we have session as a covariate, and session here is a factor. So if we have 2 sessions, we have session 1, it's going to be our reference level, and then this is the difference between session 1 and session 2. So these are contrasts. So the way we write this out in oSCR is just using session as a magic symbol. Let's call it that. It's an automatically recognized word in the oSCR fit function that's going to automatically fit a session-specific model. You don't have to provide any covariates. It's all built in the background when you create a multi-session SCR frame and state space object. So you can think of this as like an ANOVA-like analysis where you're estimating group-specific estimates here. So we've got these intersects, which are the estimates of the parameters for the first session. And then these slopes here, there's actually one for every other session. So all sessions other than the first one, we're going to get an estimate for. And these estimates that we get on the slope, these slope parameters here, are called contrasts. So this is very much like an ANOVA where you'd essentially estimate group-specific means, except here we're adopting a contrast formulation. So if you wanted to know what the estimate of session 2 was, you'd have to add session 1 to the session 2 contrast, because these contrasts are how much the other sessions differ to the first. So this is standard GLM type analyses where we use a design matrix and identify the reference level and then the contrasts. So what happens now is that yesterday we were at this situation. We had no flexibility to fit any models because we were only dealing with SCR not. There was no options here. Now all of a sudden we've developed this multi-session structured data object, which means we have access to session-specific models. And what that means is we have several modeling options, and each one of those modeling options could be thought of as a competing hypothesis. So because they're a competing hypothesis and we're using a likelihood-based modeling framework here, we could think about using multi-model inference and comparing models using AIC. So immediately by having these additional options, we have some interesting statistical problems to solve. And one of those is which of the models is more supported by the data. But I guess more directly is the fact that as soon as you can parameterize these models differently because you have the structured data, we start to get lots of different options for modeling. So we can model density as fixed across all sessions, or we can model a session-specific density, so where we're estimating a density for each of the sessions. Likewise, we can do that for detectability, and we can also do that for the sigma parameter. And we can actually do all combinations of these. So we actually are faced with quite a few modeling options and some interesting questions to potentially answer. So how do we do that in oSCR? Well, again, it probably won't be a surprise that we have some functions that are going to help us do this model comparison. Fitlist.oSCR, modcell.oSCR, and macof. So this is basically a helper function that helps you package up fitted objects, models that you fit. So maybe these models that I spoke about in the previous slide. ModCell is kind of the main multi-model inference function where it's going to take each model, it's going to take a fit list, and then it's going to rank those models according to AIC and spit back an AIC table, the thing that you see in most papers these days. And then we have this model average coefficient thing, which you can use to take a first look at variable importance and model averaged entities. Okay, so what the fitlist function does is just takes all of the models that you fit and that you want to compare, and it just wraps them up into this specific class of a list with a specific class that the next function is going to recognize. What it also does is it has this convenient argument here for rename. So regardless of what you call the models, when you fit multiple models, if you specify rename equals true, then the function is going to look within the guts of the fitted model and come up with a sensible name for your model so you can identify it, so you don't have to write out a whole bunch of stuff. The modcell.oSCR is essentially a function that's going to take this fit list object and then it's going to turn it into a processed AIC ranked model table. And then, so you can access the AIC table, but you can also access the full table of coefficients. And I'll show you that in a second. And then the last function here, macof, this is a function just that will take this coefficient table, weight them according to their AIC weights and do some kind of model averaging, not the model averaging that we'd like to do, the model average predictions, but these are model averaged estimates. So you don't necessarily want those, but you can get them. What's really nice is that this spits out a relative variable importance value, which is essentially AIC weighted measure of importance of each of the parameters across your whole model set. This will become more apparent when we start diving into an actual example, which is now. Yeah, so I'm going to go on and talk about this redback salamander study that I did when I was a postdoc in upstate New York, working with Andy and Angela Fuller. And what I would do is go out on the weekends and go and collect salamanders. So essentially what this ended up being is a really terrific data set for teaching and understanding spatial capture-recapture models. And the way the system was set up, essentially I would go out and I had in Ithaca I have these 4 trapping arrays. And what a trapping array was a 5 by 10 grid of little wooden boards, so 10 centimeters by 10 centimeters. Each of those boards was a meter apart. So you can see here, there's the grid of my cover boards in a nice open space in a forest where these terrestrial salamanders live. There's my wife helping me out begrudgingly on a Saturday morning. And then here's a picture of 2 of these little redback salamanders under one of these boards. So we flip these boards, we capture the salamanders, put them in a bag, mark them with these fluorescent paint markings. So then when you shine a black light at them, they glow whichever color combination we put, we injected into them. So we have 4 colors, including a no color. We have these 4 positions. So we actually have a ton of unique identifiers. So we essentially do this mark recapture, but it's spatially explicit in that we're catching individuals under different boards quite regularly. So the arrays are identical arrays, but they are independent. These salamanders, the individuals don't really move between the arrays at all, within the season or even between the season. They're more than 20 meters apart. In fact, only a pair of them are within 50 meters. The rest of them are well beyond the dispersal capability of an individual salamander. So essentially what I have is this really nice session structured data set. So I have 4 studies of salamanders, basically. I have 4 of these arrays. So if you do data RBS underscore ecography, this is the data set that is with the ecography paper detailing the package. So if you look at the top and the bottom of this RBS encounter data frame, you can see I have my individuals here. I have the occasions, I have the board that they were captured under, I have the sex information as well, and then I have the session ID. And if I look at the bottom of this object, you can see that these EDFs are ordered by session. So the top part of this EDF is my first session, site 1, which is actually P1A, and my 4th session is P2B. So I have a pair, so P1A, P1B, P2A, P2Bs. So I have 4 sessions here. I'm just showing you the top and the bottom to show you session 1 and session 4. So I'm just showing you 6 records from this big data frame. And then what I also have is a TDF for each one of these. So each one of these arrays, they all have identical boards, A1 through E10, and they all have the same relative coordinates. So A1 is always 0, 0, and A4 is always 0, 3. But the thing to notice here is that here's just the top and the bottom. So I have 50 boards in each of these arrays. So that's why the first 6 values go from 1 to 6, and the tail, or the bottom of this data frame, is 45 through 50, and that's E10. And you can see the coordinates there. If I look at the second TDF, so this is the second array, what you'll see is the difference here is that I have day 1, 2, 3, 4, 5, and 6. So these are covariates, and I'm going to come back to this in a little while. You can see here that session 2 only had 5 days. So I actually made 6 visits to the first board, for the first array of boards. For the second array of boards, I was only able to do 5 visits, and this is just stuff I did on the weekend. So the number of occasions varies between session, or varies between arrays. So if I were to try and put these TDFs on top of each other, they differ because they have different number of occasions. And I'll come back to how we format this TDF, but that's why we have it as a list instead of an appended data frame like the EDF. So here's session 3's TDF, and then here's session 4's TDF. So session 4 I only actually went to 4 times. Okay, so now, like I said right at the top, it's very easy to construct a multi-session SCR frame in exactly the same way as we would do any other SCR frame. What I'm going to do is provide the RBS EDF that's there in the RBS ecography data object. And then I'm going to put each one of these TDF files in a list. So that's the trapping object for each of my 4 sessions. And then I'm just going to tell data to oSCR which columns are my relevant columns from the EDF. And what I decided to do is just show you some different ways of doing this. So sometimes you might have to look, say, okay, session is my first column, individual is my second column, so I'm going to put that there. Occasion is my 3rd column, so I'm going to put 3 here. And board is my 4th column, so I'm going to put trap column 4. Here what I'm doing is just using some a little bit more R coding to identify which columns are which. So if I use this which function, I'm asking which of these column names has the name session. So column names in session is going to return me a logical true or false. And then which, the function which, is just going to tell me which value of that is true. So essentially this is going to return a number, the number that I want. So session is 1, session is 1. So this command here is just going to return a 1. So yeah, that's just some R coding stuff if you want it. Okay, so I had to provide my multi-session EDF, my extended list of TDFs now, 1 for every session. This is the same. I just provide the columns for where my relevant information lies in the EDF. Now I have to specify how many occasions for each session. And as you saw before, I have variable number of visits to each array. I have 7 for session 1, 5, 6, and 4 for session 2 through 4 respectively. And then I know in this case where I just have a standardized array across all 4 of my arrays, I can just say repeat 54 times because I know there's 50 cover boards in each of my arrays. In a camera trapping study, you may not have the same number of cameras in different sessions. And then I can just extract that SCR frame. So here we go. That's how easy it is to create the session-specific SCR frame. Just using the same information, but just acknowledging that there's a few things that need to be extended. The TDF object needs a trap deployment file for every session. I need to tell it how many occasions for each session and how many traps for each session. And the reason we need this is because essentially data to oSCR is going to create this relational database, or this relationship between the EDF and the TDFs, using these as checks. And essentially it's going to produce information under this, the SCR frame is going to contain all the information about where individuals were captured, but we have that already with the EDF. But by kind of relating all of this information together, we have the full spatial information about where things were captured, where things weren't captured, and also when and where things were and weren't captured. So we can use our standard data that we collect in the field, pass it to this helper function, and develop under the hood this expanded full information data. Okay, so if you remember from yesterday, if we just type the name of the SCR frame, it just spits out some summary information. So the thing to see now is that if you type the name of a multi-session SCR frame, you get a column for each of the sessions. So now we can see that I caught 77 salamanders in that first array. there's 50 traps, that's the same across, and this is the information that we've provided. You can see that there's variation in the number of individuals I captured. I also have the capture information, so on average, how many times was an individual captured in each of the sessions, and then for those that were captured multiple times, on average, how many were they those were captured, how many times, how many traps were they captured in, sorry, and then the mean maximum distance moved within each of the sessions. Then also there's a pooled MMDM there returned as well. Okay, and then we can also use the visualization function, the plotting function. We can just provide the multi-session SCR frame, and it will produce multi-session spider plots, essentially. You can see these are much richer than the simulation study we had yesterday, or the bear study that we looked at, because I just captured tons of salamanders. But the information content is the same. Points are individuals. Colors link individuals to where they were captured, colored lines. Okay, now we're going to make our multi-session red-backed salamander SSDF, or state space object. And remember I said before, if you provide a multi-session SCR frame, you automatically get a multi-session SSDF. So that's exactly what I'm going to do here. I'm just going to provide that SCR frame that I created in the previous slides. I'm going to define a buffer. So here I'm defining a buffer of 5 meters. And it's maybe I assumed that this, yeah, so maybe I didn't make this explicit, but this buffer and this resolution has to be in the coordinates of the traps. So my traps were relative coordinates, but they were in meters. So everything was meters. So now when I specify a buffer and a resolution, I need to specify those relative to the coordinate system I used in the, not the coordinate system, but the coordinate units that I used in the trapping object. So I'm making a 5-meter buffer around my array, and I'm going to fill the array with a uniform grid spaced 1 meter apart. And then I can plot that thing. So if I just provide the state space object to plot, it shows me my state space object. I can add the SCR frame, and it shows me the layout of the traps. And then I can also specify spider equals true, and now I get this kind of full, rich information about my state space, my trapping array, and all of my captures within the trapping array. So this is really a nice visualization of what the model is going to be working with here. Okay, then we can jump on to start fitting a bunch of models. So yesterday we were restricted to M0 because that's all we knew about. It's like, hey, we can only fit this one model. Chris hasn't told us about anything else yet. So now I've told you that actually there's this magic token that you can use, session, and you can use that for any one of the model components. So now all of a sudden we have access to 8 competing models, where we have the null model here. I'm going to call it M0. All the way through combinations of session-specific parameters to the full session-specific model. So you can see here, M1 just has session-specific detection. M2 has session-specific sigma, but constant everything else. And then I have 2 session terms. Then I have all of the session-specific density here with the same structures. So now I have 8 models. So what do we do with that? Well, we're going to, first of all, inspect each of those models just to give you a sense of, with all statistical modeling, as a matter of fact, you essentially, when you have these functions that are built to fit models on your behalf based on the specification that you provided, what you should get is summary tables that are in no way a surprise to you at all. So there should always just be a row per parameter that you're interested in estimating. So here's a good example. We have the null model where we specify d tilde1, p0 tilde1, and sigma tilde1. This is the intercept only model. This is the null model where we're just estimating 3 parameters. The intercept for density, which is like the density per pixel, assuming every pixel is the same. Likewise, for detection probability, we're saying there's no variation in detection probability. There's just one baseline detection function, and there's no variation in any way in sigma. So it's no surprise then that we have these 3 rows, which are just the intercepts. So these are estimates of the intercept on the linear predictor scale. So there's these negatives again that we saw yesterday. Then the associated standard errors, and then things like the p-value that you might be interested in reporting. P-value isn't necessarily interesting when you just have intercept-only models. It's effects that you might want to look at the p-value for. Okay, so let's look at a little bit more of an interesting case. So here's the case model 4, where we specified session-specific density, but a null model for baseline detection and a null model or the intercept-only model for the sigma. So by writing this model out, d tilde session, and knowing that we have 4 sessions in our model, without looking at the model table, I should know that I'm going to have an intercept, which is going to be an estimate of the first session's density. And then I'm going to have a contrast for all of the other sessions. So I know I should have 4 density rows in this model output. And then because I have the intercept only model for these 2, I know I should have a further 2 rows, which are going to be the intercept for detection and an intercept for sigma. So most modeling packages that you use, whether it's a GLM or an LM or even unmarked for that matter, you'll get these summary tables that are just telling you the numbers that you asked for. So here we have 1 row, the intercept only for detectability for baseline detection, 1 row for sigma, and here, just like I said, I have these 4 parameters that are related to density, this is d beta. So d naught is on the linear predictor scale, so we still have to back transform this onto the real scale. But this on the linear predictor scale, this is the estimate of the density for the first session. And this here is the difference between session 2 and session 1. So we can see, because this is a negative, we know that our estimate of density in the second array is lower than the density estimate of the first array. And then the session 3 term here, this is the difference between session 1 and session 3. And this is the session 4 term here, is the difference between session 1 and session 4. So this is what are called contrasts. So if we add these 2 together and then exponentiate that, we'll get the estimated per pixel estimate of density for session 2. If we add these 2 together. Okay, then the same thing follows for if I fit this model. So I'm saying, okay, I have a constant density model. So I should only have 1 density row here, and there it is. It's just the intercept. But I have a session-specific baseline detection model or a P0 model. So I know because I have 4 sessions, I should have 4 rows here: the intercept or the reference level, and then these 3 contrasts. And the same is true for sigma. I have these 4 sigma rows. And I might be interested in looking at the p-values of these p-naughts, or maybe density is more interesting. I might be interested in saying, okay, well, is this difference significant at the p equals 0.05 level? Well, I see that the difference between site 1 and site 2 is not, if I use that alpha level. Whereas the difference between site 1 and site 3 is significant if I'm using p equals 0.05. Okay, so what about this full model, model 7, which is the fully session-specific model? Well, the same thing holds true. I specified a session-specific density model, so I should have an intercept and 3 contrasts. The same is true for baseline detection and sigma. So I should have 12 parameters, and sure enough, if I count up the rows in my summary table, I have 12 parameters. The intercept, which is the estimate of the reference level for each of the components of the SCR model, and then the session-specific contrasts for each of those. So what I want to do is just really emphasize that these are just standard summary tables that you would get in most typical statistical software packages or fitting functions. So we try to keep in line with what you'd expect to see from a GLM or from an unmarked model, for example. Okay, so which is the model of choice here? So we fit these 8 models. Which model is the best model? Or we could ask that slightly differently if we're all biologists here. So we can, instead of talking about models and parameters all the time, we can ask which of our competing hypotheses has received more relative support using, for example, AIC as that metric. And the way we can do that is use some of these helper functions. So what I'm going to do is package up all of the models that I fit, M0, 1, 2, 3, 4, 5, 6, and 7, so the 8 models there. And I'm just going to package it up in this fit list so I can plug it into some helper functions downstream. But what I do want to show is why I put this rename argument in here, because if I didn't, then you just have model 1, 2, 3, 4, 5, 6, 7, and 8, and that's not really very intuitive. But what you do know is that there's information in the model about what model was being fit. So if I say rename equals true, then what it does is it just adds a tag onto each of the models to give you a more explicit definition of what model that is. There's this ASU row here. So there is a 4th model component which is related to a cost function, and I know a couple of people have asked about that. So if you're interested in least cost path modeling in spatial capture-recapture, which is essentially relaxing the assumption that distance is the same in all directions, you can fit in a 4th model component which is related to the cost function. So by default, the cost asymmetric space use, that's why it's called ASU. By default, that thing comes out. So if you do see it, it'll always be 1 unless you're actually doing some cost function modeling. There is an option to say drop.asu equals true, and then it throws it away, so you don't have to get confused by this like thing that's hanging around. So what this function does is essentially takes your list of models and packages them up in a nice fit list and renames them, so the next things that you could do are a little bit more intuitive than just, what was model 3 again? I don't really remember. And you'll notice that this isn't a ranked table. This is just in the order that you provided. So you can see there's variation in the difference in AIC values. So typically, lowest AIC is best. And what we tend to do is try and rank models according to their difference. So this is a relative measure. So we typically try and rank them according to that measure. And that's actually what the next function does. So there's no sorting here. There's just some nice packaging and formatting of the fitted objects. What we can do is pass that fit list to the mod cell function and then inspect that object, and what you end up finding is, or what you end up getting is a nicely AIC ranked model table. So you have your log likelihood, you have the number of parameters in the model, your AIC scores, your delta AIC, so the difference between this model and the top model, the AIC top model. Then you have this AIC weight and the cumulative weight. So these are things that you might be used to reading in results sections of papers. So this is just a way of getting exactly that information for your particular analysis. Again, keeping in line with typical statistical analysis workflows. So we can actually look a little bit deeper into, so this spits out, when you type out the name of this mod cell object, it will just spit out a nice neat table. But if you want, for example, numbers to a few extra decimal places, you can actually extract the AIC table from this. So you just have a little bit more information there. And you also get this really nice table of coefficients. So there's each column is one of the parameters that were fit in any of the models. So every parameter that was estimated in your model set has a column here. And then each row is a model. And then in these cells are basically filled with the parameter values. So you can see here that the intercepts they always have an estimate. So every model has an estimate for an intercept, and that's correct. But then for models that weren't session specific, for example, so here's P0 session 2, this model just had a fixed detectability. So there's no session 2 estimate here. So what I'm going to do is just tie up some loose ends on the modeling of detectability, and then I'll leave you with an optional exercise that you can do, you can start doing in a break that we have between now and the next lecture, or mostly I just put it in there so that after the workshop you have some stuff to do, the same with yesterday's lecture. So what I spoke about yesterday is really this bullet point here, is that there's in the TDF, the trap deployment file, we have a row per trap, and then there's these columns that you must provide in a TDF. That's the detector name, the X coordinate, and the Y coordinate of each of the traps. But what you'll commonly find, and these are directly related to questions that were asked after yesterday's lecture and over the last 24 hours, is that you do have other information. Almost always you have this other information, which is this operation matrix data, basically a recording of when a camera went down, when a camera malfunctioned, or in the Salamander study, when a board snapped, or when a bear just walked away with a board and left it 100 meters away with a steaming dump on top of it. That wasn't there to make a capture. So we need to record whether or not traps were operational. And the one way of doing that is to have this binary trap operation data. The second thing is that not all of your traps are the same. So some traps can be set in, or some detectors can be set in different types of habitats. You can even use different models or different materials. At the same time, not every occasion is the same. So you can have a lot of rain in one week and not a lot of rain in the following week. And it's reasonable to assume that detectability is somehow related to the conditions in that particular occasion. So what I want to do is just talk about how we'd add these two pieces of information into the TDF, the trap deployment file. So here, and I'm just going to use this using absolute dummy data. I'm just going to make TDFs that are just pure dummy data, just to really just to show you what the structure is. And I think knowing the structure, you can construct it yourself with your own data quite easily. So here's the minimum requirement, the TDF min, I've called it. We have the detector name, the X coordinate, and the Y coordinate. And it always has to be in this order, first, second, and third column. So that's the minimum requirement. This first extension, or this first data addition, is the trap operation data. So essentially, I'm just going to call it here O.1, O.2, all the way up to O.k. So K we typically use to indicate the number of occasions. So let's say we had 5 occasions. I've got a column 1, 2, 3, 4, and 5. And the number of columns is associated with the number of occasions. So if this trap operation is included, it doesn't have to be included. If in my Salamander study, none of the boards ever got taken away, or none of the boards were rendered useless at any point. So I never had to provide this trap operation matrix. But if you do have situations where you rotate traps or you have malfunctions, then you might want to provide this information. And if you do provide it, you need a column for every occasion, and they're going to be just appended right next to the X and Y coordinates. So they're going to be columns 4 through 4 plus K in your TDF. And if that sounds a little bit abstract, here's what that means. So here I've got a 3, I guess I should have made these more consistent. So, well, they are consistent. So, but K here is 3. So I have a column for every occasion. And then if it's a 1 in this column, then trap 1 was operational on the first occasion, but trap 3 here was not operational on the first occasion. So of these first 6 traps, only trap 3 wasn't deployed on the first occasion. And the reason we provide this information is that the fitting function is just going to identify that and say, well, I'm not going to call this not capture. I'm not going to say I didn't capture anybody on this occasion. I'm going to acknowledge the fact that there wasn't a trap here at all, or a detector here at all. So that's how we provide the trap operation matrix. And this is where you can see why TDS don't get piled on top of each other, because if I have a 2-session study where there's 5 occasions in one year and 1 session and 3 occasions in the other, these don't really stack on top of each other very nicely. Okay, the second example is how to include trap covariates to the TDF. And there's two main types of trap covariates. First is the fixed site attribute. So for example, habitat, which habitat did you put your hair snare in? Or what model did you use for, which camera trap model do you use? Now, the big thing to know about adding trap covariates is that we put in a separator into the TDF, and the default is a /. So you'd have a column of /, and then data to oSCR interprets everything to the right-hand side of that column of / as trap covariates, and anything to the left-hand side of that as either coordinates, a name, or the trap operation information. So we use the separator to just let data to oSCR know how to handle the data either side of this slash, this / or the separator. So fixed covariates are those that don't vary by occasion, and they're just provided as a single column after the / column. So here's the example habitat. So this is what a TDF would look like if you just had a habitat column and no trap operation matrix. So I have a detector name, the X coordinate and the Y coordinate. Here's my separator. Then I have this single column saying trap 1 was in good habitat, trap 2 was in bad, 3 good, 4 bad, and so on. So that's how you add trap-specific time invariant covariates to the TDF. The second type of covariate we might want is the time varying covariate. This is temperature or rain or things like that, things that vary at a trap through time. And in fact, these can vary at a trap and through time. So you'll see here that not all of these traps have the same rain variable, and they don't have the same difference in rainfall over time. So the way we provide these time varying covariates is, again, they appear after the separator column. This is telling data to oSCR, this side is trap covariates, this side is structural information about cameras or detectors, sorry. And then we have a column for each occasion. Again, we have 3 occasions here. And the thing we have to know is that we need to keep the names the same. So they're all called rain, but then they need to be indexed by which occasion they are. So rain.1, data to oSCR is going to know that is the rain variable for these traps for occasion 1. .2 for occasion 2, .3 for occasion 3. If you had 100 occasions, it'd be 100 of these columns. And then the full extended structure of a TDF, so just to summarize here, the trap operation information comes after the trap coordinates, but it comes before the separator. So data to oSCR, if it sees anything after the 3rd column and before the separator column, it just assumes that this is trap operation information. It will just do that automatically. Time invariant trap covariates are a single named column. So this stuff here. This doesn't change through time, and oSCR is going to, data to oSCR is going to know that because it's just a covariate name with no index after. Time varying trap covariates are k named and numbered columns. So we have 3 occasions here, 3 occasions. So anything that's time varying also has 3. So rain.1 for the first occasion, rain.2 for the second occasion, rain.3 for the 3rd occasion. The trap covariates come after the separator. And then this is an important point that multi-session objects must have the same covariates. So if you measured rain in one session, you have to measure rain in all of the sessions in order to fit a multi-session model with rain as a covariate on detection. Okay, so once you've got your TDF set up, the only difference then in terms of creating the SCR frame is just these last 2 new arguments here, where the first argument is specifying what are the names of those covariates that you want data to oSCR to recognize and to format so that they're available for model fitting at a later stage. And you'll notice here that we have rain.1, rain.2, rain.3, and HAB. We don't have to provide rain.1, rain.2, rain.3. The indexing is implied, so we just have to apply supply rain and HAB. Data to OSCR is going to go and look at anything that's called rain, and if it's got an index after it, it's going to say, okay, this is time varying. If it doesn't have an index next to it, it's going to say this is not time varying, and it's going to do all of that under the hood. And just notice here that I've just kind of reverted back to specifying the columns directly. And then the second thing, if we use a different separator, so say for example I used S or some other character here, I recommend just using this /. So the / is by default, but if you use something else, you can define what the separator column has in it. And that just tells data to OSCR, here's the separator column, anything to the right of that is covariates, anything to the left is structural information about the trapping. So that's it. So that's those extra information. So I hope that answered some of the questions that came up about trap operation data and covariate data. So I think what I'm going to do is I'm just going to talk through what I had in mind with this exercise, and people can do it in their own time if they want. Again, this is just an opportunity to have something to do after the workshop to get your teeth into the material a little bit more. So the optional exercise is to try and understand or dig into temporal patterns in salamander surface activity. So we having studied them for quite a while now, we know that salamander detectability varies over the course of sampling season. At the end of the season, when it's either really hot or really cold, we capture very few individuals. And at the beginning of the season, depending on which season we're sampling, it can be super cold or super hot, and we get fewer individuals. And really, this reflects some kind of thermal optimum of surface activity for salamanders, where they come to the surface and they move around at intermediate temperatures. Temperature tends to increase through the season. So what we end up doing is, in addition to collecting information on actual temperature, we just record which day of the year, and we assume that that's a good proxy for temperature, knowing that temperatures increase over time in the spring, and they decrease over time in the fall. So basically we argue, or I argue for this particular exercise, that it's sensible to model detection detection as a function of time. Really what we're asking is, does the probability that you detect an individual change over the time period of the study? So if you look at this RBS TDF that I showed you before, what you'll see here is that there's the trap ID, there's the X coordinate, there's the Y coordinate. Here we have this separator file, and then I have all of these covariates where I have day, J day, which is Julian day or ordinal day, and J day 2, which is the squared version of J day. So just a bit more detail there. J day is a scaled ordinal day, where 0 is the first day of the, or day 0 of sampling, and a unit of 1 is day 10. So every 1 unit represents 10 days. And then the covariate J2 is the squared version of that scaled ordinal day. And the reason we're interested in having a squared term is that allows us to model nonlinear effects, so quadratic effects. I can provide more information about what quadratic effects are if you need that. But the ability to estimate these nonlinearities means that we could potentially use this as a model for finding a thermal optimum. On what day do we have maximum surface activity? And that might be reflective of this thermal optimum. So the data challenge, or the analytical challenge for you when you have some time, is to go back and create the Salamander SCR frame, but providing JDay and JDay 2 as covariates. So going to the data to OSCR function and trying to create a SCR frame that has the covariates built in. And then fit a model with the quadratic effect of day on detection only. So this is a kind of a pseudocode for how you'd specify a quadratic effect. And I can answer questions about that later if you want. And answer the question statistically of whether or not there's whether the effect of day is linear or nonlinear. And whether it's nonlinear will depend on the significance of that squared term. If it's a positive, it's going to increase more than linear. If it's negative, it's going to decrease and bring the relationship back down. And then once you fit that model, can you derive, using the getReal function, what day is the high, what day do we predict activity is highest? And we can measure that by saying what day is detectability highest. Okay, so that's the end of that. I think it's probably a really good time for a break. Then Andy will pick up on modeling variation in density.